So today for computer organization and architecture, we'll cover memory. So the objective is, so we'll look into the concept of hierarchical memory, understand how each level of memory contributes to the system performance and how performance is measured. Also look into the concept behind cache memory, virtual memory, memory segment, paging, and address translation. So memory is in the heart of our stored, program computers. Before we looked into the way that memory was built, and it's accessed by various ISAs. So in this chapter, we'll focus on memory and get a clear understanding of the analysis of system performance. So there's two kinds of main memory. You've got RAM and ROM. One is random access memory. The other is read-only memory. So, and within RAM, there are two types of RAM. You've got dynamic random access memory, and you've got static random access memory. So the difference is dynamic RAM has a capacitor that slowly leaks their charge over time. Dynamic RAM is lower cost as well. So SRAM has a circuit that's similar to what we looked at in chapter 3 of a D flip-flop. So SRAM, you can think of it as very fast memory. So ROM, it doesn't need to be refreshed. So ROM is used to store permanent or almost permanent data or semi-permanent data. So generally speaking, as it says, faster memory is more expensive than slower memory. So as you know, to provide the best performance at lowest cost, organizations look into the lowest cost. Small, fast storage are kept in the CPU. Larger, slower main memory is accessed through the data bus, and so forth. So larger permanent storage in the form of disk tape is still further from the CPU. So this kind of gives you a pyramid of what's going on. Storage organizations. Sorry about that. Let me see if I can zoom in here so you can see the pyramid a little better. So as you get higher up the memory, you see how much faster it gets, so forth. And also, as you go higher up the pyramid, it's more costly than you, as opposed to going down. So we're looking into the memory hierarchy that involves registers, cache, main memory, and virtual memory. So registers are storage locations available on the process itself. Virtual memory is typically implemented using a hard drive, so it's extended the address space of the RAM. So virtual memory provides more space, cache memory provides speed. So this is kind of the steps that it takes to provide a particular piece of data. So CPU first sends a request to the nearest memory. If data is not in cache, so cache is usually very fast memory. So then main memory is queried and so forth. So we're kind of looking at the performance aspect of memory. So once the data is located, then the data and the number nearby are fetched into cache memory. So here are some definitions. You can look at hit, miss, when data is found, miss when data is not found, and it goes into some more details here you can take a look at. So entire block of data is copied after a hit. So this is the principle of locality. Three forms of locality. You've got temporal locality, spatial locality, and sequential locality. So the purpose of cache is to speed up access. Like I had mentioned earlier, it's you can think of it as a very fast memory. So cache is smaller than main memory. So here are some ways that cache mapping works. It goes into more detail here on this slide, and some more detail of how it's directly mapped and how it's accessed. You can take a look at these examples here. Direct mapping, cache memory. So it goes into some more details of different examples of how it's accessed. So you can take a look at these examples. A number of block access that it accesses. So direct map cache maps memory blocks into modular fashion. So that means the number of bits in memory address, the number of blocks are in cache, how many addresses are in the block, and so forth. So here it goes into some more examples that you can take a look at, accessing memory and so forth. So it has plenty of examples. I'm not going to go through every single example, but you can look at these examples on your own time on the slide. So there's plenty of examples here. So here are different address references, binary address, hit or miss, and it has these comments here of what's going on. Talks more about cache memory. So a replacement policy is invoked when it becomes necessary to evict a block from the cache. So different transactions that do take place. Least recently used algorithm keeps track of the last time the block was accessed and evicted the block. So information is kept about the block. First in, first out. This is a popular principle that's used. So the block that has been in the cache, they use the longest regardless of when it was last used. So then they have the random replacement policy does what its name implies. It picks a block at random to replaces it. So first in, first out, FIFO, as it's known, is one way. Then it goes into other examples that are used. So you can take a look at these examples. Talks about the disadvantages of this particular example. So how you can improve cache performance. So we're always concerned about performance. So here it goes into strictly inclusive and exclusive cache. So cache guarantees that all data in the smaller cache also exist. Then exclusive cache permits only one copy of the data. So it goes into, here it talks about virtual memory. So we get into virtual memory. So cache memory is enhanced performance by providing faster memory. So virtual memory enhances performance by providing greater memory capacity. So it goes into some more examples of virtual memory, where virtual memory and main memory are divided into equal sizes. So it goes into more examples, the slides. So you can take a look at some of these examples. And processes. An illustration that it has here of how virtual memory works. Some of the real world example by taking a Pentium architecture. So take a look at those. So computers is organized in a hierarchy with the smallest and fastest memory at the top. As we saw in the pyramid structure, cache memory divides fast access to main memory, while virtual memory uses disk storage to give the illusion of having a large main memory. So virtual memory is kind of like added on to main memory to kind of give you more memory. So cache maps block of main memory to block the cache. So there are three general types of cache: direct map, fully associative, and set associative. So fully associative, you've got associative cache with virtual cache, and you got these other policies that we learn: LRU, FIFO, LFU. So virtual memory has to deal with fragmentation, internal for page memory, external for segment memory. So I didn't keep this video long, so you can kind of get an overview. I'll provide some additional information on memory to accompany this video. Thank you.